Okay, and let's go to the desktop, and I want to remind everybody what the plan is. So here's the plan. We've already done questions on web work, and let's go through the number theory slides. So you have this on your system, on your CoCalc system, under slides / day 2. I'm just going to go to the local version on my computer. Okay. Okay, so here we go. So we talked about modular arithmetic last time, but chapter 1 actually spends quite a bit of time on modular arithmetic. So I'm going to spend a lot of time on it too. It's very important for the course. All right, so we'll go here. We didn't do these slides from last time. We will talk about XOR, but this semester we're going to do it next. So modular arithmetic is a way of mixing bytes that has a lot of applications in cryptography. So this is sort of the basic theorem and number theory that makes modular arithmetic possible. It's called the division theorem. And even though it looks a little bit weird when you say it like this, you guys started studying this in like in 3rd or 4th grade or something. So when you take any whole numbers, so take any integers n and m. So there's some number of times that m goes into n evenly. So the number of times that m goes into n evenly is q. And then there's going to be some remainder, which is possibly 0. If m goes perfectly evenly into n, then the remainder is 0. So the remainder is something between 0 and m. So we're allowing these, integers can be negative. That's why there's the absolute value sign here. But r is going to be strictly less than m, because if r were bigger than m, then you could make q bigger. Then you could factor the m out of these two parts, and then q would increase. So it's necessarily the case that the remainder is between 0 and m. So here's an example. So 36 goes into 1045 29 times evenly with a remainder of 5. So you can do those two operations. So here I've got double division. In Python, that's integer division, but in C or C++, division is integer division, so you just would do 1/. So this 29 that I put here is the Q, and this 5 that shows up here is the R. So that's the remainder. Okay. Right. So when we do modular reduction, we implicitly kind of apply the division theorem and then just record the remainder. So what is 129,837 modulo 21,398? Well, you figure out the number of times it goes in evenly, and then you take the remainder. By the way, this is why on a computer modular reduction takes about the same amount of time as division. It's because it figures it out just using long division. And then we would write that these two things are equivalent modulo 21,389, or congruent. And what that means is that if you divide them both by 21,389, the same remainder occurs both times. So 21,389 goes into 1449 0 times with a remainder of 1449. 21,389 goes into this number 6 times with a remainder of 1449. So either way, you get the same remainder, and that's why we say that they're congruent. So 6 is the number of times it goes in evenly, and 1449 is the remainder. Okay. So this is just terminology about modular arithmetic. So this number n is called the modulus. So that's what you mod out by. And we're going to be doing a lot of arithmetic modulo n. It's like regular arithmetic, but you ignore everything except the remainder. And so you might think, isn't something bad going to happen if you do that? So it's kind of a miracle that this actually works out. And we'll talk about why it works in a couple of slides. Um, so what it means to be equal modulo n is you have the same remainder when you divide out by n. So this is when my daughter is 4 and she's learning about even and odd numbers, and she's basically learning how to do arithmetic mod 2. So all odd numbers are 1 mod 2, and all even numbers are 0 mod 2, because 2 goes evenly into every even number, but 2 has a remainder of 1 when you send it into any odd number. And sort of here's the explanation why it's true. So if you look at an even number is a number of the form 2m. So 2 goes evenly into 2m. So when you have a modular expression like this, any term that contains the modulus itself, like this term 2m contains the modulus itself, which is 2, that part is always going to be 0. The modulus itself is like 0. So multiplying by 2 is like multiplying by 0. So down here, this is sort of 0 plus 1 equals 0. All right. So modulo 2, there are really only 2 numbers. This is actually an important group in cryptography. So Z2 denotes 0, 1. And when we're going to do a lot of XOR, so we'll talk about that more later. So let's just take the XOR of 2 binary numbers here. Let's say I take the XOR of, what is this? This is 13, and this is 6. So let's say I do 13 XOR 6. Then the result is 1, 1, 0, 1. So one way to think about what happened here is in each column, I'm adding mod 2. So 1 plus 0 mod 2 is 1. 0 plus 1 mod 2 is 1. 1 plus 1 mod 2 is 2, which is 0. 1 plus 0 mod 2 is 1. Okay. All right, so here in these little blurbs like this, I'm trying to make a point about modular arithmetic, which is important. So here I've got some expression, which is 4 plus 5 times 19 plus 777. So we could just do all that using a calculator. And then after we fully compute it, then reduce modulo 2. Another thing that we could do is first reduce modulo 2, and then do the arithmetic, and then reduce mod 2 again in case it adds up to more. And what you'll find is that this always gives exactly the same answer. And this is important because this second approach for big numbers is like enormously more efficient. So we're going to be dealing with digits in cryptography that are, with numbers in cryptography that are thousands of digits long. So if you can reduce those before you start doing arithmetic operations, it speeds things up incredibly. And that's really the only reason that cryptography is sort of, that you can do some of the operations that you need to be able to do. So I'm going to try to make this, always give examples. So when you do modular arithmetic, you can reduce at any point. So before you add anything, you can reduce. And then after you get done, you reduce again. Let me clear all this stuff. Okay. Right. So you can sort of write down every possible equation that you might see in mod 2. There's something like this. So here's the times table. This is the times table mod 2. And here's the addition table mod 2. So addition, this is the same thing as the XOR operation. And multiplication is the same thing as the AND operation. Actually, that's worth making a note about, right? So multiplication mod 2 is the same thing as AND. That's the condition that both things have to be true. This is the truth table for AND. This is the truth table for exclusive OR. Okay, so the only way you get a 1 here, exclusive OR is like a difference detector. So it puts a 1 in the places where two things are different. Okay. All right, so this is just saying, I'm just making a note here. This kind of proves what everybody learns in elementary school. Odd times odd is odd. Even times even is even. Odd times even is even. Even times even is even. Okay, and then there's a proof. Maybe it's good to go through this. So this is how you would formally prove that this is true. So here is some odd number. Here's another odd number. So what happens if you add these two things together? You can recollect, or manipulate these so that these two ones go over here to become a 2. And then from these other parts, you can factor out the 2 they have in common. And it turns into this. And notice every term here has a 2, and so it's equal to 0, or congruent to 0. Because remember, 2 is like 0 mod 2. And 2 and 0 means even. So this is saying odd plus odd is even. And then the other ones are similar. All right. So here I allude to like equivalence classes. And so this is sort of, we just write, when we work modulo 2, we're just talking about 0 and 1, but there's a sort of a fancier way to understand what's happening here in terms of equivalence classes. And so I hesitate to mention it because it's quite complicated and it will never be relevant to anything that we do, but let me just go over it here a little bit. So the pure math sort of fancy philosophical way of looking at what we're doing here is this 0 sort of represents the infinite family of all even numbers. So this is an equivalence class. So every number in this equivalent, maybe I should I'm writing 0 here, but let me just put these sort of scary signs on it here, just to make the point that it's not really a number, it's some kind of weird thing. This is another reason it's bad to do this, because it makes people scared for no reason. So this is kind of like the collection of all even numbers. So next would come 0, and then 2, and then 4. Okay, so this is an equivalence class because every number in this set is equivalent mod 2. And so there are other, in this case, there's exactly 2 equivalence classes. So the evens and the odds. So here are the odd numbers, -3, -1, 1, 3, etc. So now every number in this class is equivalent modulo, modulo the modulus. So this is what we're going to identify with this other symbol. And so then the meaning of like 0 plus 1 or anything plus any other thing is that you take any representative of the equivalence class. So you can take any representative here, like let's say 2 is a representative of this class, and you add it to any representative of that class. So if I actually do add 2 and -3, then what I would get is -1, okay? And then I look and I see which equivalence class the answer ended up being in. It ended up being in the odds. And so that means that the answer is that equivalence class. So I represent that entire equivalence class like this. Okay, so that's kind of beautiful, right? If you like pure math and infinite sets and things like this, this is candy. But if you find it confusing, then you can completely ignore it and just understand us to always just be talking about z2 equals 0, 1. Okay, so now we can look at the integers mod 5. So the integers mod 5 are these numbers. It's really, the 5 equivalence classes. But we're just gonna think of them as being these integers. So we're talking about Z5 here. So Z5 is 0, 1, 2, 3, 4. Right. Notice that 5 is a prime number, which turns out to be important. So arithmetic mod 5 is going to be special because 5 is prime. And we'll see more about that as we go along here. Okay. All right, and I think I got kind of carried away with evens and odds here, and let's just ignore that slide. That's kind of embarrassing. But this is important. So I said earlier that when you're doing modular arithmetic, you can do the modular reduction at any period or at any time, and this is kind of a proof of why that works with respect to multiplication mod 5. Okay, so let's just see what happens here. So we'll take two numbers. So this one happens to be in this equivalence class, so it has a remainder A. And this one is in the equivalence class corresponding to B. Possibly A and B are the same, we don't know. So this just stands for two numbers, right? This could be anything. Like for example, if one of the numbers is 13, then it would be 2 times 5 plus 3. And so the A value would be 3. And if one of the other numbers were 6, then this would be 1 times 5 plus 1. And then the B value here would be 1. So if you multiply these things out, you'll see that when you just FOIL it, everything has a factor of 5 except for the product of the remainders. And remember, 5 is like 0. So all of these things get canceled out. And the only thing that survives is the product of the remainders. So this is what makes modular arithmetic be like a nice mathematical structure. So if you take the product of two numbers and then reduce mod 5, that's the same as first. What if we first reduced mod 5 before we did this operation? Then it would just be A times B, because these 5 parts would be dead. But that's exactly the same thing as what we get anyway. So what this is proving is if you reduce before you do the multiplication, it doesn't matter, because either way, AB is the only thing that's important. If you reduce first, you get A times B. If you reduce second, A times B is the only thing that ends up being non-zero. Okay. And the same thing is true with addition. So you take some number plus some number, then everything gets destroyed except for the sum of the remainders. So you might as well have reduced first and then just added the remainders in the first place. Yeah, and this is just showing, an example. So this is reducing second, this is reducing first, and it gives the same result. Let's look at some multiplication tables. I was too lazy to write a Python program that actually printed out a multiplication table. So often you see these things written like this. So the multiplication for multiplication table for Z mod 5 would be 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. And then you fill this in just like in elementary school. So you have rows and columns. And what this means is 0 times 0. So 0 times anything is 0. I should use a different color. These are all zeros. And you get all zeros here. And with 1, 1 times anything is itself. And now you do 2, 4. 2 times 3 is 6, which rolls over and becomes 1. 2 times 4 is 8, which rolls over and becomes 3. 3 times 1 is 3. 3 times 2 is 1. 3 times 3 is 4. And 3 times 4 is 2. And 4 times 1 is 4, 4 times 2 is 3, 4 times 3 is 2, and 4 times 4 is 1. I want to just point out some nice structure here that, you know, it seems like it didn't have to be the case that the universe would work out this nicely, but it did. So this has something to do with group theory and the reason that groups are nice. We'll just ignore these zeros. These things are just kind of an ugly distraction here. And look at these numbers. What you'll see is all of the non-zero numbers show up exactly once. So here they come in the standard order. And then in these other rows, they're permuted, right? Everything shows up exactly once, and there's kind of a permutation. So this is sort of always true. Like if we use this notation, 2 times Z5, this is like 2 times A, such that A is in Z5. And this is multiplication mod 5, so we do the reduction. What you do if you do this is you get Z5 just in a different order. So like here's what we're exactly talking about is this row. What if I multiply every element in Z5 by 2? Then I get exactly the same set of numbers, except they come in a scrambled order. This is very relevant to cryptography because permutations are a key part of doing cryptography. I'll clear all this. Okay, and there's the addition table. The addition table is less interesting. You should draw it yourself. What you'll notice is that it's much less random looking than the multiplication table. Those permutations in the multiplication table, they seem to be sort of like pseudo-random reorderings of the set. But just like in the Caesar cipher, what these are is just shifts. So for example, if you do 2 plus Z5, so this would be, you know, 2 plus A mod 5 for all the A in Z5. What you would get is just the elements of Z5, but in a slightly different order. So 2 plus 0 would be 2. 2 plus 1 would be 3. 2 plus blah, blah, blah. So here's, you know, the pattern, right? So this would be 0, 1, like this. So what it is just a circular shift. So the permutation is much less pseudo-random. And so for the things like cryptography is supposed to be about confusing people, and multiplication is much more confusing than the transformation that multiplication does is much more confusing than the transformation that addition does, because addition is just a circular shift. Right. So here's a fact that we can prove. So everybody learns this in elementary school. I don't know, it's probably known by somebody before Gauss, but you know this, right? A number is divisible by 3 if and only if the sum of its digits are divisible by 3. So, you know, is this divisible by 3? Well, you just add up its digits, 1 plus 2 plus 3 plus 9 plus 1 plus 2 plus 3, and it'll sum up to 21, and then 21 is divisible by 3, so the answer is yes. But then you can also quickly see that this number is not divisible by 3 because its digits add up to 64, and 64 is congruent to 1 mod 3, so 3 does not go evenly into it. So why is this true? So this is also just kind of a good review of the decimal number system. So what does it mean? The place value number system means, you know, 1, 2, 3, 9, 1, 2, 3, that means 1 times 10 to the 6th power, plus 2 times 10 to the 5th power, plus 3 times 10 to the 4th power, plus 9 times 10 cubed, plus 1 times 10 squared, plus 2 times 10, plus 3 times 1. Now, what we're going to do is, look what happens if we reduce this entire expression mod 3. So, so we said that we could reduce at any time, right? So if I want to do 10 to the n mod 3 is the same thing as 10 mod 3 to the nth power mod 3. And so what is this? This is, you know, the remainder when 3 goes into 10 is 1. So this is 1 to the n mod 3. And 1 times 1 is just itself. So this is 1, okay, mod 3. So 10 to the n for all of these n's, these actually just become 1s. So all of these become 1s, 1 mod 3. So if we reduce this number mod 3, what we get is the sum of the digits. So this is where the sum of the digits comes from. So here is the sum of the digits because all of these things that all of these multiples of 10, they're all becoming 1. So then you add these up, and now now we want to know, is this congruent to 0 mod 3? So that's what we wanted to know about this question in the first place, right? Is it divisible by 3 is the same question as, is it congruent to 0 mod 3? So we'll take this expression, which is equivalent mod 3, and we'll ask, is that expression congruent to 0 mod 3? But that's just asking, is it the case that the sum of the digits are divisible by 3? So we just proved why that rule works. So any number is divisible by 3 if and only if the sum of its digits are divisible by 3. I love that fact. Okay. So this is just introducing some terminology. It kind of irks me that the book introduces this in the first chapter because we don't use it again until the 4th chapter. So you'll just have to kind of tuck this away. But a ring is a collection of objects, which for us will, I think, almost always just be these numbers, z mod m or something. It's a collection of objects where you have some notion of plus and some notion of times. So you know the integers themselves are a ring. So these things, you have -2, -1, 0, 1, 2. So you can add and multiply these things, and then the addition and multiplication has certain good properties like distributivity and the existence of additive inverses and some other good things. And so a ring is sort of anything that's kind of like the integers in the sense that there's addition and multiplication defined, and they behave nicely with respect to one another. Okay, so if that doesn't quite make sense, it's because it's impossible for it to make sense to you, because when you're a math major, it takes a whole semester to understand what this means. So we just have to be satisfied with partially understanding it unless you want to go deep into the theory, and then you would be in a different class. But for our purposes, being a ring just means that you can do addition and multiplication. So here are the nice properties that the operations will always have in a ring. So all operations are associative. So remember what this means. It means it doesn't matter the order in which you multiply. All operations are commutative. This is just because addition and multiplication are commutative. That means it doesn't matter which one you do or which way you do it. 0 times anything is 0. And negatives exist. So for any number a, there exists a number b such that a plus b is 0. So this b is like negative a. So that's actually what we mean by negative a. So let's look at this. I don't know. Let's just make up an example. So here's one. Let's let m equal 7. So 7 is going to be the modulus, and a equals 2. Okay. Then 2 plus 5 is equal to 0. So it's kind of like negative 2 is 5. You could also say that negative 5 is 2. So this is what negative numbers will mean in modular addition. Negative numbers are just, the rule actually is very simple. So the negative of a mod m is a minus, sorry, m minus a mod m. Notice that that's true here. So m is equal to 7, a is equal to 2, and what is 5? 5 is 7 minus 2. And it has to be that way because a plus m minus a is congruent to m, which is congruent to 0. And so there's always going to be exactly one solution here. So everything is exactly one negative. If you suppose that there was another number, man, am I going to regret doing this? Say that there's a plus b1 is congruent to 0, and also a plus b2 is congruent to 0. Well, then you can add m minus a to both sides, and then you get that b1 is congruent to m minus a, and also that b2 is congruent to m minus a. So that means that b1 was equal to b2. So inverses, negatives are unique. There's only one negative, which is this guy. Right. So that just says what I just said. All right. So because negatives exist, you can solve certain equations. How are we doing on time? Pretty good. So what if you want to solve this equation? Then you just subtract 17 from both sides. So you get x is congruent to 4 minus 17, mod 7. And then you get minus 13. And then how do you convert that back to 1? You just add something that has a factor of 7 in it. So this has a 7 in it, so it's like adding 0. And this is 1. So that means that negative 13 is congruent to 1. And you just solved for x here. So 1 plus 17 is congruent to 4 mod 7. We just solved this equation. It has to be the case that x is equal to 1. So you can solve modular equations just the same way you solve non-modular equations, by moving things between both sides of the equal sign and by canceling things. Right. So here's an example. Right. So we just did negatives, but what about reciprocals? What we're doing here is we're telling you all the ingredients that you need in order to be able to solve equations. You need to be able to create negatives or use negatives to move things around the equal sign. Now you also need reciprocals to be able to cancel numbers like this. Like if I'm going to solve this equation, I need to cancel that too. So the way that you do that in the real numbers is you just multiply both sides by the reciprocal of 2. Which is in the real numbers, it's 1/2. So this is in the real numbers, which is not the same as modular arithmetic. So all numbers have reciprocals. That means numbers that cancel them. And so, but do we have reciprocals in Z mod M? So often we do. So what would the reciprocal of 2 be in this equation? So you need something so that when you multiply both sides by that thing, the 2 gets canceled. So I would do, 2 inverse 2, x is congruent to 2 inverse mod 7. And then x would be equal to 2 inverse. But what is 2 inverse? So it's kind of funny because 2 inverse is just exactly x here. But so this is the thing such that when you multiply it times x, you get 1 mod 7. So often you can figure this out just by guess and check. So try 4 here. So then 2 times 4 is 8, which is congruent to 1 mod 7. And so x here has to be equal to 4. So the 4 works, and mod 7, that will be the only thing that works. Okay. So this is just emphasizing here that what we're calling the reciprocal, it behaves like the reciprocal of 2 in the sense that it cancels 2, but it's not literally 1/2, right? It's not literally 1/2. This is just a metaphor. So the reciprocal of 2 modulo 7 is 4. By the way, this won't always work. Notice that 7 is prime. That's important. Maybe I should just follow here and keep going. So if an element has a reciprocal, it has only one. It might not have a reciprocal, but if it does have a reciprocal, it has exactly one reciprocal, or inverse. I should start using the official term, which is inverse. And this is a proof by contradiction here to show that that's true. So if A had two distinct reciprocals, B and C, then it would be the case that B times A is the same thing as C times A, which is 1. That's just the definition of the inverse. But then you could apply B to the right-hand side of all equations. And so what would happen if you did that? You would get BAB is congruent to CAB, which is congruent to B, right? And then you would have, so we know that B is an inverse of A, so this just becomes 1. So then what you get is B is congruent to C. And so they are the same. So this is just like the uniqueness of negatives. Reciprocals are also unique. So another way to say reciprocal is multiplicative inverse. So if a number has a multiplicative inverse, it has a unique multiplicative inverse. I feel like a lot of, I can't see anybody's body language or anything like that, but I just kind of feel like people must be kind of lost. So let's do another example here. Let's make m equal 12, right? And let's just pick some number, mod 12. I'm going to pick 7. Okay. So what is 7 inverse mod 12? So the thing that makes 7 inverse is that 7 times this missing element, whatever it is, has to be congruent to 1 mod 12. All right, so how can I figure out what this is? So I could just start trying things. Like I could try a equals 0, that obviously doesn't work. 1 obviously doesn't work. 2, 7 times 2 is 14, which is 2, so that doesn't work. 3, 7 times 3 is 21, which doesn't work. 7 times 4 is 28, which doesn't work. 7 times 5 is 35, which doesn't work. 7 times 6 is 42, which doesn't work. 7 times 7 is 49, which actually does work, right? So 7 times 7 is 49. 12 goes evenly into 48, so that means the remainder is 1 mod 12. So this is an example of a number being its own inverse. So 7 inverse is just 7 mod 12. So we just found the reciprocal using this brute force procedure. It turns out that there's a much faster way to do it, which is basically the Euclidean algorithm. So the next couple of slides are just showing how slow this brute force method is. Let's go on here. Right. So let's say that I have a brute force search for the inverse of 12 to 33. So this guy modulo this other guy here. So this just goes through and it looks for it exhaustively, and it takes 292 milliseconds. And if you add up all the time that it took on This is how long it took if you're looking at a clock on the wall. That's why they call it wall time. So altogether, it took 296 milliseconds, which is long. That's unacceptably long. Then if I increase the modulus by an order of magnitude, so this modulus is about 1,000,000. What if I increase the modulus by a factor of 10? So now this is about 10 million. Then it goes up to 2.5 seconds. So that's very, 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 very slow. Okay. All right. So I also wanted to point out here that sometimes multiplicative inverses do not exist. We've talked about this several times. So before we did m equals 12, and we picked 7, and then we found the inverse of 7. But 7 is relatively prime to 12. The GCD of 7 and 12 is 1. So 7 has an inverse for that reason. But if I pick something that has a factor in common with 12, like 6, for example, and if I try to find 6 inverse, what I'll find is that it just doesn't exist. And I have a proof of why that's true in a second. So what if it did exist? So here's another proof by contradiction. So BWOC, by way of contradiction, let's assume that 6 does have an inverse. Then what's the bad thing that happens? We know that 6 times 2 is 12, which is 0. But then if this is true, then I can apply so supposing by way of contradiction that the inverse did exist, then what I would get here is I could multiply both sides by the inverse, and what I could prove then, after these cancel and this becomes 0, this proves that 2 is equal to 0. But 2 is not equal to 0, and so the assumption cannot have been correct. So 6 has no reciprocal, or no inverse. And that's the basic thing that happens whenever the GCD is not 1. Then there's some product that is equivalent to 0, and then you can prove something is 0 that's not really 0. So, so a number has an inverse if and only if it's relatively prime to the modulus. Okay. Right. So this is just explaining why the in that previous example, the inverse failed to exist, because these two numbers do not have GCD1, they have GCD3. That's why failure occurred. But success occurred here where the GCD was 1. GCD is 1 because they have no factors in common, no prime factors in common. All right, and so here's a formal proof. I did an example with 6 and 6 inverse, but this actually gives the proof here. So it turns out that for A to have an inverse, we must have the GCD of A and M equal to 1. So why? So this is a proof by contradiction again. So suppose that A is has a GCD which is not 1. Okay, so A has a GCD which is not 1. So that means there's some equation so that you multiply two things together and get 0. So A times M divided by D is the same thing as, you can just move the D over, that's just basic algebra. And then this is equivalent to 0 because M is 0, mod M. So what you get here is this. So now if you suppose by way of contradiction that the inverse exists, then you can multiply both sides by A inverse here. So over here, this is A inverse times 0, but that's just 0. And so what you get is that M divided by D is congruent to 0, which is not true. And so that means that the assumption that the inverse existed must be false, and so the inverse does not exist. Okay. So it turns out that if the GCD is 1, then the inverse does exist. So that's a different proof, and it's the proof is to give an algorithm that does it, and the algorithm that does it is the extended Euclidean algorithm, which you might have, I think you studied it before in 204. So here's some code I stole off the internet for computing the extended Euclidean algorithm. So you put in two numbers, A and B, and what it gives you is the first output is the GCD, which in this case is 1. And then it gives you these numbers, which are called the Bezout coefficients. And the meaning of those things is that if I write like, so this is X, so they're calling this X, and they're calling this Y here. So the Bezout coefficients have the property that if you do A times X plus B times Y, you get the GCD. So for this particular example, this is kind of tedious to check, but it would be true if you checked it that 239487 times its Bezout coefficient, which is 26095,389. If you took that number and then you added it to this number, 98372,498, times its Bezout coefficient, which is negative 63529, then what you would get is a number which is equivalent to 1. Sorry, it's not equivalent to, it's literally equal to. Literally equal to 1. All right. So there's always they call this some linear relation between two numbers in the GCD. So you can always do some X, you can put in coefficients here, which are the Bezout coefficients that express the GCD as a linear function of the two numbers when you're taking the GCD. And by the way, so that gives, man, I wish can I undo that? Control Z, it's not working. But if you look at, so I had something times this times that, right? This times that plus this times that was equal to 1. So now if this is the modulus, and I reduce that expression modulo the modulus, then on one side of the equation, I just get 1, and on the other side of the equation, I get this product. And anyway, this is the key, so this first Bezout coefficient, the Bezout coefficient corresponding to this thing is its inverse. You can see that that's true right here. The inverse of 239487 modulo 98372498 is the Bezout coefficient. So that's why the extended Euclidean algorithm computes the inverse. If you're completely perplexed by that, it's okay, because we're going to do a whole lecture on the extended Euclidean algorithm. All right, so look how much faster this is. So do you remember what it was before? We had like, when the modulus was on the order of 1,000,000, this took 250 milliseconds. And when the modulus was on the order of 10 million, this took like 2.5 seconds. But now, just using this crappy Python code from the internet, it's not optimized at all. If you do a similar problem, right? So this is actually bigger than any modulus we've encountered so far, because we did it with 10 million before, right? That 10 million was the one that gave us 2.5 seconds. But this is 98 million, which is almost an order of magnitude bigger than that. But now it takes 47 microseconds. So this is like a factor of like, I don't know, 1,000 or something, or more. It's like and asymptotically, it's just there's sort of infinitely faster asymptotically. It just grows. So the complexity of doing it this way, it grows as the natural log of n. So the number, I don't know if you guys know big O notation, but the number of operations you need to do it this way is on the order of natural log of n. And to do the brute force way, it's on the order of, what did you have to do? You just had to check everything. So big O of n. And you know the limit as n goes to infinity of n over natural log of n is infinity. So for big numbers, the stupid approach is sort of infinitely worse than the smart approach. kind of amazing that Euclid figured that out so long ago, or whoever the source was. And is this the end of the slides? I think this is the end of the slides. All right, I'm sure you guys are happy about that. So I couldn't see anybody's body language. I know from delivering lectures like this in the past that that was probably almost completely incomprehensible. Hopefully it will pay off in the long term, I guess. And if you're still confused, maybe what you should do is just read chapter 1 of the book, and then you can be sure that you know exactly what you're supposed to know.
Professor, I have a quick question.
Sure.
I went on the project description and the date was dated from 2019. Can you just tell me the due date for this year?
Oh, really? So let me go to CoCalc here and check this out. This is project 1?
Yes.
Okay. Oops. Oh no, I clicked that stupid thing again. I think I am going to have to click it though. Sorry. I know that shows you guys' email address. I'm not going to put this on the open internet. I mean, it'll be on YouTube, but you have to have the link to view the video. So we go to assignments and then project 1. And it says due date is 2 weeks from now. And what does this say? It says September 17th, 2020. So that's the correct due date. I think what probably happened is on the PDF, I didn't change the PDF, and so the PDF still has a different date. I'm sorry about that. But this is the true due date, which is September 17th, 2 weeks from today.
All right, thank you.
Okay, anybody have any other questions? If there is anything else you want to talk about, I'll be here for a while at 1:30. I don't know how many other students are going to show up, but you're welcome to come at 1:30. And also you can come to the open office hours of Usama. So Usama has put up another post before. So so it looks like he's got a little bit of a donut hole in his support. So he won't be back online until Sunday. So that's too long for you to wait. What is that? That's 3 days from now. If you really need to talk, remember that you can always, if you're working on project 1, you can always ping me on CoCalc by opening your chat window. And then it's most helpful if you do this in the same directory with your code, and then you say at Hunter WTF, this sucks, or whatever you want to say. And then I'll get an email notification and I'll click on it and I'll come back here and tell you what the problem is. So that is maybe like resource number 1 when you're struggling with the code. Maybe I should stop sharing. Okay. All right. So I know that was tough, and it was kind of abstract. We had to talk about what a field was, but we can't really say what a field is. There was like a rushed introduction to group theory that it should really be presented over the course of an entire semester to math majors, and several other things made that really hard to understand. Like those proofs, proofs don't really matter, but I did some proofs. And then the extended Euclidean algorithm, I went over it in like 1 second, as if you're supposed to understand that, and you're not. So that was just kind of a survey. Just think of that as like an introduction to things to come, and it's all explained nice and slow in the textbook. And just focus on your assignments and you'll be fine. Any chats? No chats. Okay, I'm gonna stop it then. It's good to see, oh wait, there's a chat. Okay, bye. Good to see everybody. I'll be here at 1:30 if you have a quick question. All right, bye.